Okay, thanks for making it to the last lecture early in the morning. So this will be dedicated entirely to these new direct detection kind of proposals. So my goal here is to do some simple calculations or examples to give some intuition for the kind of things that are out there in the literature, things like electron scattering in various condensed matter systems or atomic scattering and so on, and production of phonons in various crystals. So I'll just focus on doing a couple of toy calculations to help you get some intuition for what's going on in these calculations. They're really, sometimes you open them and maybe if you're not in this field, you're not sure exactly what's going on, and they're not really as complicated as they might look if you haven't looked at it before. And so the idea of all these proposals is to detect the kind of sub-GeV sectors we talked about on Wednesday. So just as a reminder, I'm going to put them up again. We identified a couple of thermal or quasi-thermal relics. So one was thermal freeze-out through a dark photon. And I have m-chi around, the dark matter mass around 1, or let's say 10 MeV. There was a pretty massive dark photon around 30 MeV. And I have my, I need to use V, and I have my dark photon coupling through a kinetic mixing. And then there was the other benchmark we discussed a bit, which was freeze-in. Similar mass scale and very light mediator instead. It can be as light as, say, 50 keV or heavier as well. I'm just picking this to simplify things. Okay, and similar dark photon coupling. So I have these were my processes that governed freeze out or freeze in. But through this coupling to the electromagnetic current, I do have couplings to the protons too. They're heavy, so they don't really play much of a role in freeze out or freeze in. So these, as we saw last time, these are not detectable with current direct detection experiments that focus on nuclear recoil, because most of them will have a typical threshold of about a keV, whereas the nuclear recoil maximum energy scales with the dark matter mass squared when we have sub-GeV dark matter. And I can compare that with the recoil energy of I can compare that with the total kinetic energy of the dark matter, which is just 1/2 mv squared. And so this is going to be much less than the total kinetic energy. So there's a plot that I like to show. It's a very schematic plot, but it's it's energy versus dark matter mass. And I can plot the total recoil energy the total kinetic energy, and that's going to be roughly 1/2 mv squared, so this is the line. So my keV dark matter gets multiplied by V squared. V, again, is about 10 to the minus 3, so that's going to map into about millieV. My MEV goes into EV. GeV goes into keV. So this is wow. Have you seen this chalk? Anyway.
Oh my gosh.
Yeah. Anyway.
I think that's actually that's the handle for that squeegee that is just covered in chalk.
Oh, it looked like chalk as it was like similarly covered in chalk. Yeah. It's like Jesus. Okay.
Try right with it.
Yeah. Okay, so this is my nuclear recoil. It goes as mx squared. And so we see here where, especially with keV thresholds, there's multiple challenges. There's lots of backgrounds below keV thresholds. That makes this hard. And also this energy, the deposited energy in nuclear recoils is dropping fast. So the goal of what I want to do today is explain two different other curves, one for electron recoils, which will look something like this. And one for scattering into phonons, which will look sort of like this. Okay, these are certainly not the only things out there, but these two examples are cases where we can look at a kind of a slightly different mode, somewhat different mode of dark matter scattering. And the kinematics is different such that we can now access more of the dark matter kinetic energy at this low mass sub-GeV range. So in the MeV to GeV, it'll be mostly electron recoils where we get where we can now look for these dark sectors. And I'll claim that also in the keV to MeV mass range, we can also use phonon scattering into phonons. Yes. Milli-eV. Yeah. Okay, so I'm basically going to split today up into these two parts, electron recoils and phonons. I will focus mainly, again, on the theory aspect, so I'll try to give some overview of the various different experimental directions and progress. Okay, and so I'm going to start similar to the way we did for nuclear recoils and just do some warm-up with electron recoil kinematics and what we expect. So the first thing is that the electron is not at rest. We looked at nuclear recoils and we just modeled the initial nucleus at rest and then it gets a kick. But a typical electron is not going to be in rest. It's in some sort of bound state. So let's consider just a simple atom. I don't even care. It could be hydrogen. Here's my electron. And I want to look at dark matter coming in and ionizing this atom, for instance. So this electron, because it's in a bound state, we know it's in a bound state where the size of this, the wave function will be, for a hydrogen atom, it'll be on the order of the Bohr radius. So this, I'm calling it RE. And so the initial electron, we can just Fourier transform this, has a typical momentum 1 over alpha ME. Sorry, I got these signs wrong. Alpha ME, which is going to be order of keV. So that's already one big difference with nuclear recoils. The initial electron has a fair bit of momentum, especially it can be comparable or larger than the dark matter initial momentum. And the other thing is that because it's in a bound state, we're breaking the, we can't use the free electron dispersion relation. Instead, we have some initial, okay, energy as a function of momentum, let's say. But it's not k squared over 2m. It could just be, for a bound state, a fixed number. And we have some final k prime. But again, I can't necessarily write it as k squared over 2m. So this is only the typical momentum of the electron, but since I have a range of momenta, it peaks around here. But in principle, there's very long tails, and you can access arbitrarily high momenta electron states or very low momentum electron states in the scattering. Let's see. Okay, so the thing we're working up to is we want to use the actual electron wave functions in some material to tell us about this. But again, let's just write out the kinematics first, where this is my dark matter. And I have a momentum transfer Q as before. And it's just helpful to remember, I guess, that the for momentum will be something like the energy deposited in the momentum transfer. And usually, because it's non-relativistic, the energy deposited is much less than the momentum transfer. So Q squared can be written like this. Okay, so again, as last time, I'll mainly just use the 3 momentum because in any case, the 4 momentum will reduce to that quantity. Okay, so our kinematics, well, see if I want to write it down. Okay, so now what I have is I have my initial energy, and I have whatever the the initial dark matter kinetic energy and whatever the initial energy of the electron is, and then okay, so now all the arguments we went through before are much harder they're harder to apply now because, again, I can't necessarily write this for free electron dispersion. And in the notes, which should be uploaded, it is helpful, though, to consider a free electron dispersion where the initial momentum is on the order of keV. And you can see, try to get some feel for what happens. So I'm just going to summarize the results, because I think they should be, I can argue what the results are just based on what we did last time. So what we did last time was we found when the nucleus is much heavier than the dark matter, then we just get 2 times the reduced mass V, or sorry, 2 MV. It just bounces right off the nucleus. So let's say we take the free particle dispersion. Then if the dark matter mass is much bigger than the electron mass, the momentum transfer is going to be given by the electron mass times the initial electron velocity. I guess there should be 2 principal. So that's in the case, the dark matter is the heavy target, and the electron's the light thing that hits it and bounces right off, and we get the momentum transfer set by the initial electron momentum. And this initial electron velocity is basically on the order of alpha, so it's about 10 to the minus 2. Then the deposited energy, again assuming this free particle dispersion, or let's write just, yeah, delta E. Is going to be given by this times the dark matter velocity, something like that. And that was 10 to the minus 3. So I have this almost MeV thing times 10 to the minus 2 times 10 to the minus 3. And this is going to be around few EV. So that's why in this plot above, I've drawn the electron recoils as kind of flat above or peaking at around a deposited energy of an EV. You can definitely go below, but you're starting to go on the tail of these momentum, the distributions for the electron momentum, or the dark matter momentum, either way. And when the dark matter is much lighter than the electron, then we have, again, the reverse case. The momentum's roughly going to be set by the dark matter mass and initial velocity. And the deposited energy can be of order 1/2 mx